Nowadays, we don't really have to search too hard for a motivation to study quantum physics. There are plenty of experiments happening around the world every day which exhibit quantum effects. But the situation, of course, was quite different about 100 years ago or so when quantum physics was born, when people couldn't rely on such sophisticated techniques and methods, and manifestations of quantum physics were very, very subtle. In this video, I'm going to discuss two such pioneering experiments. But before going to this part, let me tell you a little bit about the mood of the scientists back then on the eve of the discovery of quantum physics, which in fact was very pessimistic, in that people believed that there was nothing else but classical science and Maxwell's equations and Newton's equations and Newtonian gravity. So to illustrate this, so let me here present two quotes by very influential scientists, Albert Michelson and Lord Kelvin. For example, Albert Michelson in 1894 at the dedication ceremony for a physical laboratory at the University of Chicago said the following: "The more important fundamental laws and facts of physical science have all been discovered, and these are now so firmly established that the possibility of their ever being supplanted in consequence of new discoveries is exceedingly remote." A little later, Lord Kelvin says literally, there is nothing new to be discovered in physics now. All that remains is more and more precise measurement. So you can see that even the most famous and the most influential physicists didn't believe that there was anything new there, and they didn't expect anything new. As a side comment here, let me mention that Michelson actually received the 1907 Nobel Prize in Physics for his groundbreaking experiments on the measurement of the speed of light, which laid the foundation of the relativity theory. So he obviously was proven wrong by himself, actually. But back in the end of the 19th century, he and Lord Kelvin were not the only one thinking in this pessimistic way. So the reason for this was a lack of obvious experiments available at the time that couldn't be explained by the classical theory. So in some sense, you may say that the situation was similar to what's going on now, actually, with the Large Hadron Collider at CERN, where all experimental data, including the discovery of the God particle or Higgs boson last year, are actually consistent with the so-called standard model. So hopefully the situation will change soon, and there will be some exciting new discoveries, just like it did change back 100 years ago or so, when a few elephants sort of entered the classical room, by which I mean experimental data that couldn't be explained by classical theory. So here I present a list of a few such experiments, and two of them we're going to discuss later in this segment, but among them is black body radiation, quantization of atomic spectra, which we will talk about later in the course, the photoelectric effect, which showed that under certain circumstances light can behave as a beam of particles. And also there was another very curious and interesting in its history experiment, which I refer as accident in Bell Labs, shows electrons behave like waves, which normally goes under the name of electron diffraction. So I will now discuss in detail these two experiments. Philippe Lenard was a German physicist and the winner of the 1905 Nobel Prize in Physics for his work on cathode rays. But back in the beginning of the 20th century, he was studying how ultraviolet light interacts with metal by knocking off electrons from it. This effect originally was discovered actually by Hertz in 1887. It's now called the photoelectric effect, but originally it was actually called the Hertz effect. So here I present a schematic of Lenard's experiment, copied from his original paper published back in 1902. Notice the year here. In this experiment, he had two metal plates. Here is the left plate and the right plate, connected via an electric circuit. So we should imagine having an electric circuit here. And one could adjust voltage across the plates. So in the photoelectric effect, light comes in from a source somewhere here and illuminates a metallic plate. So under certain conditions that we'll discuss in a second, electrons are emitted from the metal, and if their energy is large enough to overcome the potential difference here, they reach the right plate, which effectively closes the circuit and results in a measurable electric current. So by adjusting the voltage across the plates, one can measure the energy of the emitted electrons this way. So what's very important is that if we rely on the classical theory of light, which views it as an electromagnetic wave of this sort, here's an expression for the electromagnetic wave, which we'll see actually pretty often in this course. So the classical theory would clearly predict, and this is very important, that increasing the intensity of the light should lead to more energetic photoelectrons. So the more intense the light, the higher the voltage that the electrons would be able to overcome. Also, the classical theory would predict that that intense light of any frequency should be able to kick some electrons off the metal plate. So these are very clear-cut predictions, and there was no way around them in the framework of classical physics. However, this was not at all what Lenard observed actually in his experiment. As a matter of fact, his experiment observed exactly the opposite. So first of all, the energy of the emitted electrons didn't depend at all on the intensity of the light, which was in sharp contradiction with the classical physics. And also, very importantly, no photoelectrons were produced if the frequency was smaller than a certain critical value. So if the frequency of the light was smaller than some omega critical, there was nothing, no effect whatsoever. The electrons didn't reach the right plate. And so this was a major mystery at the time and got actually Albert Einstein thinking about it. So it's probably not very surprising that this mystery attracted Einstein's attention, as he was obviously thinking about the properties of light at the time, as we know. So 3 years after Lenard's paper in the year of 1905, which is often called the miracle year, because in 1905 Einstein wrote 4 amazing papers that have completely redefined the foundations of physics. And one of these papers is this paper that we're now discussing concerning an heuristic point of view toward the emission and transformation of light. So in this paper, Einstein basically introduced the notion of a photon, which resolved the mystery of Lenard's experiment. So here I have a long quote from Einstein's paper. These are Einstein's words in the paper. So let me read it. The usual conception that the energy of light is continuously distributed over the space through which it propagates encounters very serious difficulties when one attempts to explain the photoelectric phenomena, as has been pointed out in Herr Lenard's pioneering paper, the one we discussed in the previous slide. And then he goes on to the main concept of the photon. So according to the concept that the incident light consists of energy quanta, however, one can conceive of the ejection of electrons by light in the following way. Energy quanta penetrate into the surface layer of the body, and their energy is transformed, at least in part, into kinetic energy of electrons, etc. Notice that Einstein didn't really call his proposal a theory, but rather an heuristic point of view, which it was. It was more a qualitative picture, but a very important one, because it introduced the notion of photon, a particle of light carrying a quantized energy. And so here I show a little animation which illustrates Einstein's view of what might be happening in the photoelectric effect. And in this picture we have these particles. So let me play it once again. We have these particles which essentially represent light, and each particle of light, each photon, interacts individually with electrons, and therefore only if the energy of a single photon exceeds a certain threshold, photoelectric effect would occur. And also this picture explained why the effect was not dependent on the intensity of light, or in other words on the number of photons hitting the surface per unit of time. So another important element of the theory was the assumption that the frequency of the light, omega here, was proportional to the energy, and the coefficient of proportionality between the energy and omega is, we now know, is the Planck constant. So there's actually going to be 2 notations for Planck constant. We use h and h bar, so h bar we're going to use a little more often, and the relation between them is just this numerical factor of 2 pi. And in any case, so in this picture, basically it was clear why the frequency of the light was the key. So the frequency of the light was related one-to-one to the energy of these photons, and electrons would either be able to overcome the voltage here or not, depending on whether or not the frequency was high enough. And this essentially resolved the mystery behind the photoelectric effect. So an interesting comment here is that Einstein received his 1921 Nobel Prize in Physics mostly for formally, at least, for his work on the photoelectric effect. Here is actually citation for the Nobel Prize. Actually, I think it's fair to say that for as important as this insight turned out to be, the photoelectric effect, theory of photoelectric effect, his other achievements in developing special and general relativity are even more impressive. So finally, let me mention here that ironically, Einstein, being one of the pioneers of quantum theory, actually remained skeptical of quantum mechanics throughout his life and never fully accepted it.